Okay, hello everyone. We're going to have one last lecture for today, and this is also another coding lecture. So let me share my screen and let's talk about this. This lecture is going to mostly also work with DFS. We're going to see simpler algorithms for two of the problems that we have already solved and we have already coded. So the problem of topological sort and also the problem of finding the strongly connected components in a directed graph. Now, before I continue, I have to give you some basic definitions. So the first definition is the definition of a transpose graph. So imagine that I have a directed graph G. The transposed graph of G, which is shown as GT, is just the same graph, except that I have reversed the direction of every edge. So if I had an edge from 1 to 2 here I have an edge from 2 to 1. So if G was over the vertex set V and had the edges E, GT will be over the same vertex set, but if it will have the edges ET. And the way that this is defined is that if I have an edge from U to V in G, in E basically, then I will have the reverse direction from V to U in ET. And this is if and only if. Now, based on this, it's pretty easy to see that if I can go, for example, from vertex 1 to vertex 3 in G, then in the transpose graph, I can go from vertex 3 to vertex 1. So even reachability is transposed in that sense. Okay. Now, of course, those of you who have passed linear algebra know that the reason I'm using transpose here is because the adjacency matrix of this graph is the transpose of the adjacency matrix of this one. Okay, so that's the first definition. Now, the second definition I want to give you is the DFS start and end times. Sometimes the start time is called discovery time. So this is actually a very simple concept. Imagine that I'm doing a DFS and I also have a timer. And I just increase my timer whenever I pass over an edge. And for every vertex, I remember the time that I entered this vertex. So the time that I started exploring this vertex or the time that I discovered this vertex. And I will also remember the time when I ended my DFS at this vertex. So if you want to think about the colors that we had before, like white, gray, and black, the start time is the time when my node becomes gray for the first time. And then the end time is when it becomes black, okay? So let's just do an example of this. Let's say I have this graph and I want to do a DFS. So let's say I start my DFS from vertex 1. Now, this means that the discovery time or the start time of vertex 1 is just 1. So I'm going to write it like this. Now I go to 5. So I have now discovered vertex 5 at time 2. Then I go to 6. So I have now discovered vertex 6 at time 3. Then I go to 7. So I have discovered vertex 7 at time 4. Now at time 4, I'm at vertex 7, and I see that there is nowhere else to go because I cannot go back to 5. I've already seen 5. So I've seen 2, 5, 6, and now 7. So from 7, there is nowhere to go. So I would say that this is now the end time of 7 because I'm at 7 and there is nowhere to go. So the end time of 7 would just be 4. I could also increase it and say it's 5. It doesn't really matter. So as you will see, what we will care about is mostly the order of the starting times and the order of the end times. So you can define your start and end time in any way you want, as long as you respect the order. So from vertex 7 at time 5, I finish vertex 7. I go back to vertex 6. Now my time is 6. And I see that vertex 6 is also finished. So vertex 6 finishes at time 6. Now I go back to vertex 5. I see that again, there's nowhere I can go from here. So vertex 5 finishes at time 7. And I go back oops, I didn't start from vertex 2, I started from vertex 1. I don't know why I had done that. Okay. Yeah. So from 5, I go back to 1, and I see that there is nowhere to go from 1 either. So I've seen pretty much everything I could see, everything that was reachable from vertex 1. Oh, no, sorry. Now from 5, I can go to 2. Oh, okay. This is kind of bad. Let's do this again. So at time 6, I finished vertex 6 and I went back to vertex 5. Now from vertex 5, I see that I can go to vertex 2. So I will have an edge from vertex 5 to vertex 2. And now vertex 2 has started at time 7. So I've seen 2. Now from 2, I can go to 3. So I go to 3, and the starting time here is 8. From 3, I can go to 4. So I go to 4, and the starting time here is 9. From 4, I can't go anywhere else. So I say this is the end time of 4, which has an end time of 10. And then from 4, I go back to 3. Again, from 3, I cannot go anywhere else. So 3 ends at time 11. I go back to 2. From 2, I cannot go anywhere else. So 2 ends at time 12. I go back to 5. I cannot go anywhere else. So 5 ends at time 13. And finally, I go back to 1. And there is nowhere else that I can go. So 1 ends at time 40. So you see, for every vertex, I have a starting time, and I also have an end time. And I could just calculate this while I was doing my DFS. Now, several interesting points. The first point is that you can use these starting and end points to tell whether a vertex is a descendant of another vertex. So look at this. The time period from the starting point to the end point, this time segment, this interval, is the time when I was basically exploring this vertex and all of its descendants in my DFS, right? So if the time segment for one vertex, for example, for vertex 2, is a subset of the time segment for another vertex, for example, vertex 5, then I know that 2 is a descendant of 5. Similarly, like 7 is a descendant of 6, and its time segment is a subset of the time segment of 6. And you can see it for all the pairs here. And it's not hard to prove that this holds in general. Okay, so already by just having these things, I can easily tell whether a vertex is an ancestor of another vertex or a descendant of another vertex, which might be useful in some algorithms. But then these times also give me 2 orderings of the vertices, right? So I can order my vertices based on their start time. So if I do that, I will get 1, 5, 6, 7, and then here 2, 3, 4. Okay, so this is the order based on starting time. But I can also order my vertices based on their end time. And that would give me a different ordering of the vertices. So which vertex has the smallest end time? That's 7, which has an end time of 5. So I can put 7 first, then 6, which has an end time of 6. Then I have 4, which has an end time of 10, 3, which has an end time of 11, 2, which has an end time of 12, 5, and 1. So you see, I get 2 different orders. I can order my vertices based on their starting time, or I can order them based on end time. And of course, I can also print these orderings while I'm doing DFS. So this is the concept of starting and end times. Now, I want to use this. I want to use both the transpose graph and this concept of start and end times to give you relatively simpler algorithms for topological sort, and then also for strongly connected components. So in topological sort, remember that my input is a directed graph, and it's supposed to be acyclic. It doesn't have any cycles, and I have to just print an ordering of the vertices such that all of the edges go from left to right. Okay. Now, the algorithm that we've already seen in the course was that I would always find a vertex that can go first. Now, how can I find a vertex that can go first? I can always say, if I have a vertex that has no incoming edges, it can go first. So in this case, I can say that 1 can go first in my topological sort, or 9 can also go first. And then I said that I would remove that vertex and I would continue. But here's another question. Which vertices can go last? If I want a vertex to be at the end of my topological sort, so let's say this is my topological sort, I want to see which vertex to put at the end position. Well, all the edges have to go from left to right, right? So this vertex that I'm putting at the end position cannot have any edge to any other vertex. In other words, I can take any vertex that has no outgoing edges, and I can say I put this vertex last, right? So this is also a valid algorithm. You can prove that it's a correct algorithm. So I can do the topological sort like this. I can take a vertex that has no outgoing edges. So for example, 11, and I put it last. And then I remove it, and I remove all of the edges that came into it. I find another vertex that has no outgoing edge, in this case 7, because I've already removed 11. And again, I put it last. So I can create my topological sort from the end to the beginning. Actually, let me just do this, but I just want to take a copy of my graph. Okay. So here's what I'm doing. Every time I'm finding a vertex that has no outgoing edges instead of incoming edges, and I'm putting it last. So I put vertex 11 last, and now I remove 11 and all of the edges that came into it. Now I find another vertex that has no outgoing edges, for example, 10. I put 10 last, and I remove 10 and all of its edges. I find another vertex that has no outgoing edges, for example, 8. And I remove it. And I continue like this. I find another vertex that has no outgoing edge. I can put 9. I can put 3. I can put 4. I can put 6 here, no outgoing edges. I can put 2. I can put 5. And finally, I have 1. So you see, this is also a valid topological sort, because if you consider any of the edges in the graph, you will see that they go from left to right. But the difference between this algorithm and the previous version was that now I'm creating my topological sort from the end to the beginning. Okay, let's see. Fine. But remember, we also had a topological sort algorithm based on DFS, and that algorithm was actually quite complicated, right? We had to create all these DFS trees, and there was this idea that I process my DFS trees from right to left, but then inside every DFS tree, I first see every node, and then I see its children from right to left, and so on. There were so many rules like that. So let's see if I can create this topological sort with just one DFS and without going back and processing the tree one more time again, okay? So here's the thing. Suppose that I do a DFS. I do a DFS from any vertex. I start and I keep doing DFS until I get to a dead end, until I get to a node from which I cannot go anywhere else, okay? There is no outgoing edge from this node. If there is no outgoing edge from this node, we just said that we can put this node at the end of our at the end of our topological sort. So I can just put it at the end of my topological sort and remove it. And then I can continue doing the same thing. So let me just do it on this graph. So let's say I do a DFS first from vertex 5. I can do my DFS from any vertex. I don't really care. So I start from 5. I go to 6. Now, from 6, let's say I go to 4. From 4, I go to 7. From 7, let's say I go to 11. And at this point, I see that there is no outgoing edge. Because there is no outgoing edge, I would just put 11 at the end of my topological sort. Okay, because I know that if I have a vertex that has no outgoing edge, it can always go to the end. But a very important thing here is that if I look at the starting and end times, so 5 started at time 1, 6 started at time 2, 4 started at time 3, 7 started at time 4, and 11 started at time 5 and then ended at time 6. So this vertex that I'm putting at the end is the vertex that actually has the smallest end time, okay? But now from 11, I'm going back to 7. And again, I see that from 7, I cannot go anywhere else. So 7 ends as well. The end time of 7 is 7. And I would put 7 in my topological sort as well. Again, I'm creating my topological sort from the end towards the beginning. Okay, from 7, I go back to 4. I see that there is nowhere I can go from 4. Everything is already seen. So 4 also ends. In my DFS, I get an end time of 8 for 4. And I'll add 4 here as well. Okay. Now from 4, I go back to 6. Again, I see that from 6, I cannot go anywhere else. So 6 ends. This is time 9. And 6 is added to my topological sort. From 6, I go back to 5. And now I see that there is nowhere else I can go from 5 either. So 5 ends too. 5 ends at time 10. And now I add 5 to my topologicals. Now I haven't seen all of my vertices. Let me just show what I have seen. I've seen 5, 6, 4, 7, and 11. So I'm going to do another DFS. I'm going to continue doing my DFS until I see all of my vertices. So let's say I now do a DFS from vertex 9. So I start from vertex 9, and the starting time at 9 is 11. And I can go to 10. The starting time at 10 is 12. From 10, I cannot go anywhere else. So the end time is 13. And I would add 10 here because 10 finished. And I go back to 9. Again, there is nowhere else I can go. So the end time of 9 is 14. And I add 9 here. And I've seen 10 and 9. Okay. Now let's say I do a DFS from 1. So I start from 1. I'm seeing 1 at time 15 for the first time. And from 1, I can go to 2. So 2 starts at time 16. Then from 2, I can go to 3. So this is starting at time 17. From 3, I can go to 8. This is starting at time 18. And finally, from 8, I cannot go anywhere else because I've already seen 11. So my DFS on 8 ends. So it's ended at time 19. And I'm also going to add 8 to my list, to my topological sort. I go back to 3. And again, I've seen all of these. I go back to 3. There is nowhere else I can go. So 3 ends. The end time is 20. I add 3 here. I go back to 2. There is nowhere else I can go. The end time is 21. I add 2 here. I finally go to 1. There is nowhere else to go. The end time is 22. I add 1 here. And this is also a topological sort. And you can check that it is correct. So basically, in order to do topological sort, I can just do DFS. And I can keep track of the end times. Right? And then I take the vertex with the smallest end time, I put it last. I take the vertex with the second smallest end time, I put it second last, and so on. Okay. So basically, topological sorting is like sorting based on the end time. And of course, the runtime here is just O(n plus m, because I'm just doing DFS. It's just that whenever I'm done with a particular vertex, I add it to my list. Okay, so let's code this. So I'm going to call this topological DFS. Oh, I already have that. So let's call it topological DFS 2. Actually, here's the thing. Let me copy the topological DFS that I had from before. And let's call that topological DFS 2. Okay. DFS 2. Okay. So I'm going to remove my print function from before. And I'm also going to remove children. I don't care about children. I'm going to remove parent. I don't care about it. So this as well. Let's see what I have in my main function. I'm reading the number of vertices and the number of edges. And then I'm reading the edges, creating the adjacency list. And then I say, do a DFS. So first find the vertex that is not seen and then do a DFS from it. And keep doing that until you see everything. Now, let me rewrite my DFS. So when I'm doing DFS from vertex S, I'm going to say that I have seen S. And of course, I'm going to say that for every vertex T that is adjacent to S, that is a successor of S basically, do a DFS from T. Okay. And again, I do this only if I have not already seen T. So this is my DFS, but now I want to also keep track of time. So this is very easy. I just say for every vertex, I have, let's say, a start time, and I have an end time. Write it completely. So start time and end time for every vertex. For this particular algorithm, I actually don't need to keep track of the times, but I'm going to do it anyway, just to show you how this works. And then I can just have a clock. And let's say my clock is originally 0. So whenever I enter DFS, I increase my clock. And then I say that this is the starting time of S. So a start time of S becomes my clock. Similarly, whenever I'm leaving my DFS, I increase my clock and I say this is the end time of S. Okay, so this gives me the starting and end times. Great. And remember, I want to basically, whenever I finish at a particular vertex, whenever I reach the end time of this vertex, I want to add this vertex to the topological sort. But every time I'm adding to the beginning of the topological sort. So I'm going to have, in this case, let's say a deck. And I'm going to have a deck of integers called topological sort, or just let's call it big T. And whenever this happens, I just say t.pushFront S. Okay. Now, I didn't use my clock at all. That doesn't really matter. I just wanted to show you conceptually how you can keep track of this time if you want to use it in your algorithm. In this case, I'm not really using it in my algorithm. And finally, I would just say for every vertex V in the topological sort, just write V. And maybe I can also write something like the topological sort is this. Okay, let's see G++ topological DFS2. Oh, I cannot call it clock. Oops. Yeah. So I'm going to just call it clock with big C because it's problem. Okay. And here I have to also use clock with big C. Okay. Let's do this. So I have 11 vertices. How many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so I have 1, 5, 1, 2, 1, 6, 5, 6, 2, 4, 2, 3, 6, 4, 4, 7, 4, 11, 3, 8, 8, 11, 7, 11, and 9, 10. And this is the topological sort that it created. Is it exactly the same? Yes. No, not really. So it put the 9, 10 at the beginning, but that's fine. So I can first do 9, then do 10. Then here it gives me 1, 2, 3, 8, 5, 6, 4, 7, 11. And that's correct as well. So it's a correct topological sort. And again, my runtime is just ON plus n. Now, what if I didn't want to create my topological sort from the end? What if I wanted to create my topological sort from the beginning, like before? Well, I can just look at my graph and take its transpose, and then I can run the topological sort algorithm on that. So I can just do a DFS on the transpose, and then whatever vertex has the first endpoint in the transpose is a vertex that doesn't have any outgoing edge in the transpose, which means that it doesn't have any incoming edge in the original graph. So I can put it first. So instead of applying this algorithm to the original graph and then filling out my topological sort from the end to the beginning, I could just transpose my graph and then apply the same algorithm, but then fill my topological sort from beginning to end. Okay, so let me do this actually. So topological DFS 2, I'm going to copy it into topological DFS 3. Okay. 3.cpp. Go. Okay. So I'm going to basically just show you how this changes. The only change is that I'm going to create the transpose graph. So instead of creating the original graph, I'm just going to say, do the opposite. So instead of adding the edge from U to V as you were supposed to do, add the edge from V to U. And then here, when I'm creating my topological sort, I don't need to use a deck. I can just use a vector. And every time, instead of doing push front, I just do push back, because I don't need to reverse the order. And this also gives me a topological sort. Okay, I'm not going to give it the same input again. Just believe me that it works. Okay, so this was all I wanted to tell you about topological sort. Again, it's up to you if the previous algorithm we've seen for topological sort is easier for you, or if this one seems easier. But in any case, there is this really nice relationship between the end times of DFS and topological sort. And of course, you can do the DFS either on the original graph or on the transpose graph. But now I want to go back to strongly connected components. And I want to talk a little bit about a different algorithm to find the strongly connected components. So we've already seen Tarjan's algorithm, and we saw that Tarjan could basically find all the strongly connected component of a graph using just one DFS. Now, I'm going to give you a different algorithm. This algorithm is going to use two DFSs. It's going to actually do a DFS on the original graph and then do a DFS on the transpose graph. But it's going to do it in a very nice and really clever way. So let's just talk a little bit about the intuition here. So suppose that U and V are in the same strongly connected component. Okay, so let U and V be vertices in the same strongly connected component, in the same SCC. Right? What does this mean? This means that there is a path from U to V in G, in my graph G. And there is also a path from V to U in the graph G. That was the definition of a strongly connected component, okay? So there is a path from U to V, I write it like this to mean it's a path in G. And there is also a path from V to U in G. Okay? But here's the thing. We said that if there is a path from V to U in G, I can instead say that there is a path from U to V in the transpose graph in GT, right? So I'm going to use this one. I'm not going to use this definition anymore. I'm going to say U and V are in the same strongly connected component if there is a path from U to V in G, and there is also a path from U to V in G transpose. Okay? That's pretty intuitive at this point. Now, I'm going to do my DFS on this original graph G. And as I'm doing my DFS on this graph, I'm going to also keep track of my starting times and end times. Okay? So let's do this. This is going to take some time, but I'm doing it anyway. So I'm taking this. And let's do a DFS. Let's start from the end. Let's start from vertex 11. So I start at vertex 11. It has a starting time of 1. I see that I cannot go anywhere, so it has an end time of 2. Then let's say I go to vertex 10. I start at vertex 10. I have a starting time of 3. From 10, I see that I can go to 7. So 7 now has a starting time of 4. From 7, I can go to, let's say, 9. So 9 has a starting time of 5. And I'm also marking the things that I have seen. Now from 9, I cannot go anywhere else. And because I cannot go anywhere else, 9 has an end time of 6. Right? And then I go back to 7. I see that from 7, I can also go to 8. And 8 now has a starting time of 7. From 8, I cannot go anywhere else. So this was the end of 8. It has an end time of 8. I go back to 7. I see that I cannot go anywhere else. So this was the end of 7. This has an end time of 9. I go back to 10. I see that I cannot go anywhere else. So 10 also has an end time of 10. Okay, so this is the second DFS tree that I saw. But I'm going to continue my DFS until I see everything. So I'm going to do a DFS from vertex 6 now. So its starting time is 11. From 6, I see that I can go to, let's say, 3. So I go to 3 and it has a starting time of 12. From 3, I can go back to itself, but that doesn't really help me. I can also go to 4. So let's say I go to 4. 4 has a starting time of 13. From 4, I cannot go anywhere else. So this is the end of 4. 4 has an end time of 14. I go back to 3. I see that I cannot go anywhere else. So it has an end time of 15. And I go back to 6. Now from 6, I see that I can go to 5. So I can go to vertex 5. And 5 is going to have a starting time of 16. Now from 5, I cannot go anywhere else. So it has an end time of 17. I go back to 6. I see that I cannot go anywhere else. So 6 has an end time of 18. Okay. Now, finally, I do a DFS on this last one. So let's say I do a DFS on 2, and 2 has a starting time of 19. I go to 1. 1 started at time 20. So I've seen 2 on 1. Now from 1, I cannot go anywhere else. So its end time is 21. I go back to 2. I cannot go anywhere else. So its end time is 22. Okay. Okay. So this was a DFS, and a DFS that created the starting time and end times on this graph. Nice. Now, here's the thing. Remember that we talked about the strongly connected components, and we said that every strongly connected component is going to be entirely within one of my DFS trees, right? It doesn't mean that each one of my DFS trees is one strongly connected component on its own. One tree might be several connected components, several strongly connected components. For example, here you can see that this tree has 10, 7, 9, this strongly connected component, but it also has 8, which is this other strongly connected component. But if you look at any strongly connected component, you'll see that all of its vertices are in the same tree. Now, why was this? This was because I said there are some special vertices. I say a vertex is special if it's the first vertex in its strongly connected component that is ever visited by my DFS. Now, when I reach a special vertex, for example, let's say when I reach vertex 6, and this was the first vertex in its strongly connected component that I reached, I am sure that I'm going to see everything that is reachable from 6. So I'm going to see everything in this strongly connected component. And I'm going to see all of this as descendants of 6, because by definition, 6 was the first time that I entered this particular strongly connected component. Okay? So this is also the idea that we used in the previous algorithm. So this idea that we have some special nodes. So I have 11, for example, which is a special node. Here I have 10, I have 8, I have 6, and I have 2. So I have 5 special nodes, and each one of them is the highest node in its strongly connected component that was seen by my DFS algorithm. But remember, at this point, I don't know my strongly connected components, so I can mathematically talk about my special nodes, but I don't know where they are. I don't have an algorithm to find them yet. I just know that I have these starting times and end times. Okay. Now, here's the thing. I'm going to use an ordering of the vertices similar to the previous case. But before that, let me give you some intuition about what's happening here. So take one of the roots. Take, for example, 6. It's the root of this tree, right? So because it's a root, I know that it's a special vertex. Every root has to be a special vertex. A special vertex was the first vertex that is seen in its own strongly connected component, which is also the highest vertex in the same strongly connected component. And of course, I said that my strongly connected components are always within the same tree. So if I start at the root of my tree, I'm pretty sure that the root is definitely going to be a special vertex. Okay, but let's look at the root of one of my trees. I can look at 6, or let's say I look at 10. Now, what do I know about vertex 10? I know that from 10, I can reach all the other vertices in this tree. And actually, the vertices in this tree are exactly the vertices that are reachable from 10, because I started the DFS from 10, and this is what I saw. Okay, except for, well, 11, which was in a different tree. So these are all the vertices that are reachable from 10 and were not seen before 10. So all I know is that all of the strongly connected components that contains 10 is contained within this tree. So I don't know which vertices in this tree are in the same strongly connected component as 10, but I know that it's a subset of them. And I know that all of them are reachable from 10. But here's the thing. In order for a vertex V to be in the same strongly connected component as 10, I'm using U equal to 10. There should be a path from U to V. So I know that I have a path to every node here, but there should also be a path from U to V in the transpose graph. So I can look at my transpose graph, and I can do a DFS from vertex 10 in my transpose graph. And I can see what I reach there. So if I do a DFS from 10 in the transpose graph, it means that I start at 10, and every time I'm taking the vertices in reverse order. So let's see what vertices I will see. I will see 10. Sorry, I'm taking the edges in reverse order. So I see 10. I take this edge in reverse order. I see 9. I take this edge. I see 7. I can take this edge, but it gets me back to where I was. I take this edge in reverse order. I see 5. I take this edge in reverse order. I see 6. I take this one. I see 4. I take this one. I see 3. I take this one. I see 1. I take this edge in reverse order. I see 2. So I saw all of these. And from 6, I can also No, I cannot take any edge to reach 8, and I cannot take anything to reach 8. Okay, so these edges with the red ticks, these vertices with the red ticks are the vertices that I could see in the transpose graph if I did a DFS from 10. Okay. Now, what does this tell me? This tells me that all of these vertices are reachable from 10 in the transpose graph. But I also know that these vertices were reachable from 10 in the original graph. So if I take the intersection of them, so on the one hand, I have 1, 2, 3, 4, 5, 6, 7, 9, 10. On the other hand, I have 10, 7, 9, 8. The intersection of these two sets is just 7, 9, and 10, which is my strongly connected component. So I can do this, and I can basically do it for each one of my vertices. So I can find my strongly connected components one by one, right? But this is taking a lot of time because, of course, my first DFS takes ON plus M. But then when I want to do the DFS on the transpose graph, I'm doing a new DFS for each one of the vertices, let's say each one of my roots. And when I find its strongly connected component, of course, I can remove it and then I can continue like that. But I'm basically doing one DFS on the transpose graph for each one of my strongly connected components. So my total runtime is something like this. It's K times N plus M, where K is the number of strongly connected components. So this is not good. Why is it not good? Because if I have many strongly connected components, imagine, for example, if I don't have any cycles at all, if I have a DAG, then every vertex is its own strongly connected component. Then this is a terrible time. It's going to be N times N plus N. So I need to do this in a smarter and faster way. I don't want to do this one. Okay. So what is the smarter way that I propose? I want to, of course, look at the start time and the end times. That's the whole reason why I'm doing all of this. And I'm going to say whenever a vertex ends, let's just add it to the end of my list. So let's create the same list that I had for topological sort, with the difference that, of course, here I can have cycles. But anyway, I have end times for my vertices, so I can write my vertices based on the order of their end time, right? So as soon as a vertex ends, I put it at the end of my list. So the first end time is for vertex 11. I put it at the end of my list. And what is the next end time? The next end time, okay, I have 2 here. I have 6 here. Yeah, it's for vertex 9, so I put 9 here. Again, I'm creating my list from the end towards the beginning. The next vertex to end was actually 8 with an end time of 8, so I put 8 here. Then the next vertex to end was 7. The next vertex to end was 10. Okay. Then I did this DFS, and I finished vertex 4 first. Then I finished vertex 3. Then I finished vertex 5. Then I finished vertex 6. And then I did this DFS. I finished vertex 1, and I finished vertex 2. Okay. So this is just an ordering of my vertices based on their end time. And I'm putting the smaller end time at the end. So the smallest end time was the end time of 11. So I'm putting 11 at the end. And I'm putting the vertex with the largest end time, which is vertex 2 with end time 22 at the beginning. So this is just sorted by end time. Nice. Now, here's the property that I want you to see here. What happens if I look at my special vertices? So my special vertices were 2, 6, 8, 10, and 11. Okay. Now, here's the thing. I have 2 here, and the strongly connected component of 2 is 2 and 1. And you see that every other vertex in that strongly connected component is appearing after 2. I have 6 here. The strongly connected component of 6 is 6, 3, 4, 5, and all of them are appearing after 6. I have 10 here. The strongly connected component of 10 is 7, 9, and 10, and 7 and 9 are also appearing after 10. So basically, if I sort based on this order, I know that for each one of my special vertices, all of the vertices that were sorry, I know that for each of my special vertices, all the vertices in their strongly connected components appears after them. Okay, and this is again easy to prove. I'll leave it to you to prove it. Okay, so why is this interesting? Well, because I also have another property, and the other property that I have goes back to this idea here, where I said that if you want to see whether a vertex is a descendant of another vertex, you just look at the time segments, and if this time segment is a subset of this time segment, then this vertex is a descendant of this one. Okay, but let's just look at the end times. If I just look at the end times, basically every descendant has an end time that is smaller than all of its ancestors. Again, you can check this, and it's also easy to prove based on our algorithm. Okay, so I have some special vertices. For example, I have the special vertex 8 here and the special vertex 10, and they are in ancestor-descendant relationship because, again, I did my DFS at 10, and this DFS tree contained more than one strongly connected component. But the really important point is that this one will appear after this one in the list. So 8 appears after 10 in the list. Okay. Now, so what happens if I look at my transpose graph and I do DFS, but when I want to do DFS, I first do DFS on 2, and I see which vertices I could see. And then I find the first unseen vertex, and I do a DFS from there, and so on. So I'm going to use these vertices, the vertices that I got from my first DFS on the original graph G, as the order for doing the DFS on the transpose graph G transpose. Okay? So I'm going to do a DFS from vertex 2 in G transpose, and let's see what I see there. So, okay, let me just, so can I put it here? Yeah, let me just take a copy of this. And let's put it here. And actually, let's transpose everything. So in this case, these two edges don't matter because they were each other's transpose. So I have an edge from 4 to 1. I have an edge from 4 to 3. This edge doesn't change. I have an edge from 3 to 1. I have an edge from 4 to 5. I have an edge from 6 to 4. I have an edge from 3 to 6. I have an edge from 3 to 5. I have an edge from 5 to 6. I'm basically transposing all of my edges here. Okay. Okay, hopefully I did it correctly. So now I have this transpose graph. And I'm going to start from vertex 2, and I'm going to do a DFS from vertex 2 in this transpose graph. So let's see what I see. I start from 2, I can go to 1. So I go to 1. Now from 1, I cannot go anywhere else. So that's all I see. So based on this, I'm going to conclude that 2 and 1 are in the same strongly connected component. Now, why would that be the case? Because you see 2 was the root of this tree here, this last tree that I had, okay? And 1 was a node in that tree. So when I see 1 doing the DFS from 2 in the G transpose, it means that I had a pass from 2 to 1 in the original graph, and I also had a pass from 2 to 1 in the transpose graph. So both of them are going to be in the same strongly connected component, and that's the strongly connected component that is represented by 2. So I'm going to say that they're both in the strongly connected component of 2. Now I'm going to do it from vertex 6. So I start from vertex 6, and I'm doing DFS on this transpose graph. So I can go to vertex 4. From vertex 4, I can go to 1, but I've already seen 1, so I don't go there. I can go to 3. From 3 in this graph, I can go back to 6, but I don't. I can also go to 5, so I go to 5. Now from 5 in this transpose graph, as you see, I cannot go anywhere else. So the vertices that I saw were 6, 4, 3, and 5. And I'm going to say that all of them are in the strongly connected component of 6. So I'm going to put 6 here for all of these. I'm going to say they're all in the strongly connected component of 6. Now I'm going to start from vertex 10, do a DFS again in the transpose graph. So from 10 in the transpose graph, I can go to 9. From 9, I can go to 7. And by the way, sorry, I forgot that I've seen all of these. So from 10, I can go to 9. From 9, I can go to 7. From 7, I can go to 5 or 6, but I have already seen them. So this is the DFS tree that I get when I do the DFS from 10. I'm going to say all of them are in the same strongly connected component. They're all in the strongly connected component of 10. But very crucially, I didn't see vertex 8. So that means vertex 8 was not reachable from vertex 10 in the transpose graph. So it's not in the same strongly connected component. Now I do a DFS from 8 in the transpose graph, and I only see 8. So I would say that 8 is its own strongly connected component. And the same thing happens for 11. Okay, these are my strongly connected components. Now, why is this algorithm correct? Why would this work? Because here's the thing. As I'm starting in this order, let's say when I'm reaching, for example, a vertex 6, what do I know? If 6 was really the first vertex in its strongly connected component, then all of the vertices in that strongly connected component are to the right of 6 in this order. So that means that if I have not seen 6 in my DFS before, in my DFSs, in the previous DFSs that I have done, for example, here I did a DFS from 2 and I didn't see 6. This means that I have also not seen anything else in the strongly connected component of 6. Because if I had, for example, seen 4, since 4 and 6 are in the same strongly connected component, I would also see 6. But that didn't happen. So basically, whenever I'm reaching one of these special vertices, and I don't know which ones are the special vertices at the beginning, but whenever I reach a special vertex, I know that I have seen nothing in its strongly connected component, right? So now I do a DFS from this vertex 6. The question is, why is everything that I see in the strongly connected component of 6? So I do the DFS from 6, I see 4, 3, and 5. This means that all of these vertices are reachable from 6 in this transpose graph. But don't I have to go back to my original graph and see which vertices are reachable from 6 in the original graph? Well, it turns out no. Because here's the thing. Consider the case of 10 and 8. Okay? So I look at vertex 10. And in my original graph, when I did the DFS, I could actually reach vertex 8. So there was a path from vertex 10 to vertex 8 in the original graph G, even though they were not in the same strongly connected component, right? But here's the thing. Because there was a path like this, when I did my DFS from 10, I saw 8. So 8 became a descendant of 10, which means that 8 appears after 10 in this listing. So if 8 appears after 10, it means that if I do my DFS in this order, when I get to vertex 10, I'm not going to see vertex 8. Right? Because Y actually. So let me just see. Yeah. So yes, that's correct. So 8 appears after 10 here. So remember, I had a path from 10 to 8, but I don't have a path from 8 to 10 in the original graph. So in this graph, in the transpose graph, I don't have a path from 10 to 8. So when I do the DFS from 10, I'm not going to see 8. Now, when I do the DFS from 10 in this transpose graph, is it possible that I see something outside of its strongly connected component? So for example, in this transpose graph, there is a path from 10 to 6. Is it possible that I see 6 when I do a DFS from 10? Again, the answer is no, because 6 appears before 10. Now, why does 6 appear before 10? Because of the DFS order that I originally had. So remember, I was ordering everything by the end time. So in this case, you see that from 6, I can reach 10 in my original graph, but from 10, I cannot reach 6. So it means that the end time of 6 is going to be before the end time, the end time of 6 is going to be after the end time of 10. Because either I see 6 first, in which case 10 becomes a descendant of 6, and then the end time of 6 is after the end time of 10, or I see 10 first, as happened here, but that means I will not see 6 in the same tree. So I will see 6 in a later tree, and then the end time of 6 will be after the end time of 10. So in any case, if there is a path from one vertex to another vertex, from 10 to 6, was it 10 to, sorry, from 6 to 10, but not in the opposite direction, there's no path from 10 to 6, then I am sure that this one will have a larger end time in my original DFS than this one, which means that it will appear sooner in this list, which means that when I'm doing the DFS on my transpose graph, I'm going to see the strongly connected component of 6 before I see the strongly connected component of 10. So by the time I get to the DFS on 10, I've already seen the strongly connected component of 6, and I have already marked them. So the DFS on 10 is going to only see the strongly connected components of 10. And that's why after I do this first DFS and after I create this listing, I can just do the next DFS on this listing, and I can be sure that whatever I see in my transpose graph is exactly my strongly connected components. Okay? So based on this, we now have another simple algorithm to compute the strongly connected components. And this simple algorithm is just going to do 2 DFSs. So the runtime of the algorithm is also O(n plus m), because it's just 2 DFSs and each one of them takes n plus m. And by the way, this algorithm is called the Kosaraju algorithm. Okay. So let's code this. So I'm going to call this Kosaraju algorithm CPP. Just as before, I'm going to read a graph. So let's say I read the number of vertices and the number of edges, and then I read all of my edges. So I read a vertex U and a vertex V. And now here's the thing. I have to save both my original graph G and my transpose graph. Now, in my code, I'm going to show my transpose graph just with T, not GT. So let me also include vector. So in order to save G, I'm going to have the successors of every vertex. So I have the successors in G of every vertex. And of course, I'm going to do the same thing for T, which is the transpose graph. Okay. And let's say my maximum n is something like this. Okay, when I have an edge from U to V, it means that V is a successor of U. So in the list of successors of U, I have to add V. But in the transpose graph, it's the opposite. So in the list of successors of V, I should add U. Okay, so I created both of my graphs, the original graph and the successor graph, and the transpose graph. Okay. Now I'm going to do my DFS on my original graph. So in order to do that, I'm going to just have something like this, sin G, and let's also have sin T. Okay. Now I say for every vertex I, again, the order doesn't matter. I say from n to 1. If I have not seen I in G before, in my DFSs on G, do a DFS G on I. Okay. So this is my first DFS, and I'm going to call it DFS G. So I'm going to have DFS G from vertex U. Now, let's just write the basic DFS. I'm first going to say that I have seen U, so sin G of U is 1, or it's better to write true, let's say. And then I'm going to go to all the successors of U. So for every vertex V that is a successor of U in G, let's do a DFS from V. And of course, I do this only if V is not seen. So if not sin G of V, do this DFS. Great. Now, remember, I was looking at the n times. Now, this time I'm not going to save the n times. I'm just going to save this list. So the last element of my list is the vertex that has the smallest n time. So whenever something ends, I add it to the beginning of my list, right? So let's say I have a list. I'm going to use a deck again. You can also use a vector and then reverse it at the end, but it doesn't really matter. So this is my order. Let's call it O. This is the order obtained from the first DFS. And basically the idea is that whenever I'm finished with vertex U, I do O.push front U. So I add U to the front of the list. You see, when I'm finished with 11, I add 11. And then when I'm finished with 9 afterwards, I have to add 9 before 11. So I have to do push front. And then I have to add 8 before 9 and so on. Okay, so this O is now the order that I'm going to use for my second DFS. So I'm going to say for every vertex I in O, and this goes over O in order, I say if I have not seen I in this graph T, in my transpose graph, I do a DFS in the transpose graph from vertex I. Okay. So this is DFS in the transpose graph, and I will have a vertex U. Now, here's the thing. In this particular DFS, I want to also pass it the name of the root vertex. Okay, 2. But, okay, I actually don't need that. I could save this whole list. But if I want to save the list, I have to pass the root vertex. You can do it with that or without it, it's fine. So let's just pass the root vertex as well. So when I'm doing the DFS, I know which vertex I'm at, and I know where is the root of the current DFS tree. Now, again, let's write the boilerplate of DFS. So I say that I've seen U, and then I say that for every V that is in the set of successors of U in the graph T, if V is not seen, if not seen T of V, do a DFS T from T. Okay? And great. I have to give it the same root. Now, here's the thing. I can create my SCC list, max n, and whenever I see U, I say SCC of U becomes root. So this gives me basically this list. Okay, and finally, I can just say for every I from 1 to n, just write SCC of I. Yes, SCC of I. Okay, now I could also just print them here instead of saving in the SCC. And if I just printed it here, I didn't need to pass the root. But it's your choice. You can code it in this way or that way. I can also keep track of the numbers. So let's say every time that I do a DFS in my tree T, I'm going to increase my answer. And so here I can say I found these many strongly connected components. Okay. Let's see. Let's compile this. It's compiled. Let's run it. And actually, I have this graph from before, so I can just copy this graph. Okay. And as you see, it found 5 strongly connected components. It says 1 and 2 are in the same strongly connected component. 3, 4, 5, and 6 are in the strongly connected component whose special vertex is 6. 7, 9, and 10 are in one strongly connected component as well. 8 is in its own strongly connected component, and 11 is also in its own strongly connected component. So if you remember this order, you can just do one DFS on the original graph, and then one other DFS on the transpose graph, and that would give you all the strongly connected components. Okay, have fun and see you soon.